Okay, we're now live streaming. Are you comfortable keeping the participants window open so that in case I get distracted, you can let somebody in that comes late?
Yeah, I have it open on the side here.
Fantastic. So for those of you that are just joining us, we're going to give a couple minutes to let the stragglers get in before we start our program today, Optimizing Hospitals with CodeTool. So give us about 1 or 2 minutes and then we'll get started. I think it's a good time to get started. My name is Mike Wilson. I'm Executive Director for IBIPSA USA. And with us today in our webinar series, we have Patrick Peace from CodeTool. Today, he's going to be talking to you about optimizing hospitals. I'm going to also be asking everybody to please mute themselves, and that way Patrick can give his presentation. I want to encourage you to also ask questions via the chat, and during the course of the presentation, Patrick will get to those questions in a timely fashion. Once again, Patrick Peace, Mechanical Engineering Director for CodeTool, speaking today about optimizing hospitals. And I'll throw it to you now, Patrick.
Thanks, Mike. So yeah, I'll carry on and go through kind of a brief agenda about what we're going to talk about today, which of course is optimizing hospitals and how we can do that, and a bit about why we might want to do that. And we're actually going to do kind of a worked example of, an example hospital being built in my hometown of Boston, Massachusetts, seeing how we can optimize that for, energy, carbon, cost, and daylight, some human aspects. So that's what we're going to go through today. To kind of kick things off, a bit more about myself. My name is Patrick Pease. I am the Mechanical Engineering Director at Cove Tool. Prior to this, I worked as a consulting engineer for 9 years, primarily in Boston, but also a few years in Dublin, Ireland. I'm a mechanical PE and a member of ASHRAE and BIPSA. And just a few examples of some of the projects I've worked on. This is the New Children's Hospital in Dublin, Ireland, and then ISEC, which is a laboratory building here in Boston. So a lot of high-end projects that I've been involved in. So to kick things off, kind of why would we want to, optimize a building or optimize anything really? Well, I'm sure you've seen a slide like this before. It's all about climate change. So, buildings account for 40% of emissions causing climate change, on the globe. And if you're in a city or, you look at just electricity, it's, 76%. So really reducing energy use, equating that to carbon is our goal, is to, fight climate change. Specifically for hospitals, this can be a challenge. So on the right, we see a graph of energy codes where we see, energy reduction targets. And, a lot of these have to do with more efficient systems, better envelopes, all these kind of things. And then at the left, there's all these, health and safety and kind of human health requirements for hospitals. So, hospitals are unique in that we're not just trying to, live and work, we're trying to heal in them. So the actual atmosphere within them is very important. So there's almost competing standards of, saving energy versus meeting the, indoor requirements for the spaces, for the patients, for the doctors, et cetera. So there's these competing standards and codes, as we go through to try and, reduce energy use and carbon. Also very unique to hospitals is hospitals are trying to, heal people, make people better. Another aspect of emissions, of course, is air pollution. Air pollution makes people, sick. Asthma, stroke, heart disease, all these things come from air pollution. And if we're, a hospital or healthcare organization, we, approach things from do no harm first. So being able to reduce our emissions to nothing, goes to that goal of doing no harm to our patients from the get-go. So it's another kind of key aspect of a hospital that we might want to go and reduce our carbon impact. Just some facts that I found about hospitals for 2021. So there are about 6,000 hospitals in America, which is a lot. Here's a map of them. You can see where there's more dense population, there are more hospitals. Where there's not, there are fewer. There's just under 1 million staffed beds, which is a lot. Admissions last year, which obviously connected to COVID, was over 36 million. And that number for total expenses, which includes, all expenses, is over $1 trillion. So that's a lot of zeros. This is kind of the cost that healthcare has, in the States. Another interesting fact is between 2015 and 2021, it's just a 6-year time span, we've built 36 new hospitals. So hospitals, are being built around the States, very quickly to meet needs of patients and everyone. Now, what's unique about a hospital when it comes to the energy impact? It's really down to how much energy they consume compared to how big they actually are. So hospitals only account for about 1% of the built area, but they account for 5% of the energy consumed from buildings. So this is, it's a big difference between how much land they're actually taking and how much energy they're consuming. Another key aspect of them is projects to build a new hospital take a long time, anywhere between, say, 5 to 10 years for a project. To go from concept to completion to even more, 20 years for a hospital if it's very, very large is not unheard of. And that means that if we're designing for net zero by 2030, which is a goal a lot of firms and a lot of people have bought into of a thing we need to do, designs today, in fact some designs yesterday, needed to already be net zero.
What is that?
And this really puts us at a position of needing to find how we can, optimize a project to get all the way to the net zero goal that we need by 2030 and beyond. So a few learning objectives just for this one. So we're going to go through the key metrics of optimizing a hospital, kind of look at what a workflow looks like to do that. Talk about the key stakeholders somewhat, like who in a hospital design is important. There are a lot more than, say, in a typical office building for sure. And then how can we use kind of comparative results to decide on design choices? We're not getting full answers at any time. We're trying to compare options and make decisions. So how do we actually do that? So we'll talk about that. So to kick things off, the key metrics that we're going to look at are EY, operating carbon or emissions, operating and capital costs. So how much does it cost us every year to operate a hospital? How much does it cost to build? What's the embodied carbon of that hospital? So on the opposite side of kind of use, what are the views? Like how good is our hospital? How much can we see out and improve our patients' lives? And then what's our SDA and our ASE? So what's our daylight factor? What's our glare factor? To really kind of quantify how much quality are we providing to the patients. And kind of this image here is from a project, actually that new children's project I worked on in Dublin. And you can see the focus at this early stage is really, geared toward the SDA and the views. Like this is what's important, from a patient standpoint. Like we want to provide a great atmosphere for them to heal in. So these categories are very important, and perhaps even more important in a hospital than other buildings. So the first metric that we need to look at, I'm sure everyone's seen it before, of course, energy use intensity. We're measuring energy use per area for the whole year, kilo-BTUs or kilowatt hours per area. We get this through an energy model. If you have an existing building, you could get this through your yearly utility bills for an existing building. And really, this is about comparison and benchmarking. EY allows you to compare buildings of different sizes. That's like the key aspect of it, to each other to kind of see how well you're doing and tracking towards zero. So of course, the goal is get that energy to zero. We don't want to use any energy in buildings because then we don't have to, pay for that energy. There's no carbon emissions from generating that energy, and it goes to our, future of zero carbon. So a bit about site and source, because this can be very important. For this particular presentation, we're only going to look at site EUI for a couple of reasons. It's much easier to calculate. You don't need to really know anything about the site or your utilities to calculate it. It's also probably the more commonly used. If you hear EUI and it's not specified if it's site or source, there's a really good chance it's site. So we're going to use that for today. There is an argument for using source as it is much more complete. It is location specific, and it converts the energy all the way back to primary energy only, which kind of makes it a more equitable or more equal comparison if you're really comparing energy options. The one thing I would definitely say on the site for a source argument is that if we're going to zero site EUI equals zero source EUI. So once you get to nothing, they will equal each other. So they work out in that way. And so in the next slide, we're going to look at SDA, which has a really great kind of animation, which is also a pause for some water. And so this is spatial daylight autonomy. Or more specifically, it's the percentage of floor area that's receiving over 300 lux for at least 50% of regular occupied hours. What's that mean, really? It means how much daylight is in my building, how much of the time do people in my building see the sun, see natural light, as opposed to electric light. How would we simulate something like this? It's a computer simulation is how we can do it, and there's several out there. This one, of course, being CoveTool. Why do we care about this? Because we're really trying to get happier people, healthier people. There's a lot of studies out there that look at how natural light improves people's mood, productivity, and health. So in a hospital, that's very important for patients. If we have wards where someone might be staying there many days or even weeks, if natural light will definitely help them heal. And so what our goal for this one is to maximize. We want to maximize our solar daylight autonomy. Conversely, of course, we have annual solar exposure, which is really glare. So glare is when there's too much sun, there's too much brightness, and actually hurts our eyes. So this is if it's over 1,000 lux for at least 250 hours per year. And just also conversely, we want to minimize this because glare will make people uncomfortable, make people not want to be in that space. If you were in that space and had sunglasses, you would put your sunglasses on. So we do this by, again, computer simulation. We're doing it to make people happier, and also it is attached to reducing cooling energy, because if we are reducing solar gain, which would be equated to glare as well, we're going to reduce that the cooling energy as well. So minimizing our ASE is important. The next one is operating cost. So operating cost is dollars paid for energy used on site every year. You would do it again through a building energy model, computer simulation. You could back calculate from your yearly utility bills, of course. And really, why is this important? It's because budgets are very, very much real, and perhaps more so in healthcare than anything else. This chart on the right, which is from a great resource called Targeting 100, which I definitely recommend checking out, essentially shows that for every dollar in profit or money that a hospital is made, that equals about $20 gross income. So conversely, any money saved on energy is actually 20 times that. And this means that you can really, if you're saving energy costs, that's money that can go back into the hospital to improve patient care, which is what a hospital's all about. So cutting operation cost is a goal. So that minimize is the goal for the cost. Another one that's also important for hospitals and related to at daylight and such is quality views. And these are based on the LEED view credit, which is a very helpful credit to kind of quantify what these views actually are. Like, how do we even measure good views versus bad views? And this allows us to look at our building to say, do we have good views to the outdoors? Can we see the sky? These kind of things, again, are connected to people's wellness. So again, we're going to do this with computer simulation, and the goal is to maximize. One caveat on this one is it is very important, of course, to include internal partitions when we're looking at views, because if there's a wall in the way, we won't be able to see the outside. For deep floor plans, this can be very impactful. So that's always something to think about when you're looking at views. Do you have all the information required? So do you have the internal layout? A couple more, of course, the construction cost. Again, dollars spent to construct the building. How we might get it is, a cost estimator, contractor, perhaps an automated tool to get a good estimate out. And again, it comes down to, budgets are real. Not every hospital is built by, a private institution that's independently funded. They have, budgets and limitations on what they can spend, and they want to make sure every dollar is going towards, helping patients. So again, the goal is to minimize. The last two are around carbon. So getting back to our, emissions. So operational carbon, it's, our greenhouse gas emissions from the energy we consume on the site. It's going to be CO2e, which is CO2 equivalent, not emissions, as sometimes is mistaken. And it's typically in metric tons or kilograms. And again, you can calculate this through a computer simulation, like a building energy model, or there's various tools out there like the Zero tool or other automated tools that can do this for us. And kind of why are we calculating it? It's contributing to climate change, so we want to minimize, and also that negative impact on human health. So we want to avoid as much of this as possible to improve the health of the communities that the hospitals are located in. And now we have InBody Carbon, which is definitely newer on the scene when it comes to a metric, but very much an important one in the past 10 years for sure. And really this comes down to, as we emit fewer and fewer carbon emissions from operation of buildings, the emissions that go into making the building now stand up for a lot more. So we want to minimize those as well. So minimizing the complete carbon life cycle of a building. And again, we could get this through, an LCA or a carbon calculator. And really, it really needs, EPDs. So from manufacturers, what's the carbon content of the stuff going into the building? And again, we want to minimize this as much as possible. So in summary, we want to maximize our SDA views and literally minimize everything else. And that's going to get us, the quality hospital that we want. So it's a rather simple equation of, max SDA, max views, minimal everything else. And so that's what we're going to look at in our workflow as we go forward. Before we kind of get into the workflow, I wanted to provide some benchmarking info just so we could kind of see kind of where things are at and how well we'll do in our benchmarking. So this is a chart of various hospitals in the greater Boston area. As you can see, they range from about 550 EUI all the way down to about 150. So a big range, which is an important aspect of hospitals. Every hospital is unique. They have different hours. They have different departments, which play into how much energy they'll use. The average, though, over the US is 249, so about 250 for kind of all hospitals taken as together across the US. And now kind of where's that energy being used is very important in hospitals as well. So this helps us target, what do we need to change to reduce that energy? So knowing the end use is very important. So this is a breakdown for the MGH building in Boston. It's Mass General Hospital. It's an older building, but constantly renovated. So it's hard to say how old anything in it probably is. And then from an NREL study in 2014. So we see that, yes, equipment and lights, 21%, probably expected that. Reheat and heating, it's cold in Boston, 26% kind of expected that. Some interesting ones is actually medical imaging. So we often think that medical imaging, because MRIs themselves have a huge kilowatt demand, is going to be a huge energy use. But comparing it to the overall energy use of a hospital, it's actually very small in this case. Very similarly with, say, the pumps are almost nothing. With fans added together, we get over 10%. So fan energy is very important to a hospital. For another look at that, this is a similar breakdown for a hospital on the West Coast in Washington. So a newer hospital with a lower EUI. But again, if you look at the split of, where's the energy being used, it's a lot in that reheat and a lot in our equipment and lighting. So the equipment and lighting percentage together is almost exactly the same. So that's kind of, can flag up to say, oh, I need to target this to reduce the energy for my building. But what's interesting about these two aspects is they require, coordination with the stakeholders of the hospital. It's not a simple, oh, I can buy a more efficient chiller or a better boiler and reduce these things. There needs to be, coordination with the operations of the hospital to really make an impact on these kind of things. Similarly, there again, we see imaging is only 0.8%. So again, it's not really moving the needle in any way whatsoever. So next, we're going to go through some early stage modeling. And this often looks messy. So this is just an illustration of how a workflow might look. So a lot of things we want to do, like look at HVAC options, look at envelope options, massing studies, operational options, all these things we'd want to look at. But they're all kind of a mess. We don't know which one to start with. Maybe we start with some envelope options, got some energy out, didn't do cost yet, did something else, all this stuff. And it's really moving us kind of disconnectedly away from a holistic optimization. There's no connection to our optimization. So we're going to reorder this for this kind of example and start very methodically. So we're going to start with just a few models and do a massing study. After that, we'll do a site rotation to see where that gets us. And then we're going to define several options that we want to look at, and then actually run them as bundles all at once. So we're not going to look at kind of just HVAC on its own. We're going to look at HVAC, envelope, and operations all together, get metrics out in energy, cost, daylight, all the things we were just talking about. And that's going to allow us to decide on an optimized design, a very kind of holistic approach and very ordered approach, which will help when you're doing a complex project like a hospital. So for the example we're going to do today, I've picked a location in Boston that is actually an old train yard that's earmarked for development in the next couple of years. So it's empty right now. So we're going to paw a hospital down there. We're going to do roughly 400,000 square feet of just a general acute hospital. We're actually going to start with that targeting 100. They have a Scheme A hospital, so we're going to start there as our kind of first mass. And this is concept stage. So still early on, we don't know that much about the hospital. Like we don't have an internal layout, and we don't have much else besides a shape, a size, and targets. And we're going to start with ASHRAE 90.1 2016 as our baseline. And so we're going to start with the massing, and that can look something like this, which is a lot of data, but we can unpack it slowly. So from left to right, what I have is 3 different masses for a hospital. I have a different EUI for each one, which we calculated, a different SDA for every single one, from worst on the left to best performing on the right, 24%. The red of the sun actually indicates that my ASE was over 10%, which my goal there is to be under 10%. So that's a flag that shading is going to be needed further down the road to get that ASE back down to where I need it to be. Next, we have operational costs and construction costs. So again, pretty close, but some differences there. Going from 2.6 to 2.7 in operation, and about 7.9, 7.5 for construction. Kind of important aspect here, we're looking at just equipment costs and for the HVAC and the envelope, kind of how much do those cost and compare them. We're not bringing in labor, we didn't bring in a cost estimate, these are just high level numbers for comparison. And that's kind of an important theme of this optimization. We're not trying to get the right answer for every single one of these, we're trying to get comparable answers. Then at the bottom, we have our operational carbon. So how much carbon is the energy we use emitting every year? And then the embodied carbon. So again, here, the embodied carbon, we're just going to look at the envelope because we can do that very, very quickly and kind of use that as a comparison. We're not going to worry about having to do a full LCA for every single one of these because the time required for that would just kind of sink this whole kind of approach and not allow decisions to be made. And we want to make decisions. So on that, how do we make a decision? So there's our data. How are we going to make a decision? So it's very important to prioritize metrics. We looked at several that you can use to make a decision on a project. But which one do you use? To do this, it's really about identifying the key stakeholders and getting their agreement, their buy-in on what's going to be required. So unlike an office where there might be, an owner for the building and maybe a CEO, et cetera, there's all these unique positions in a hospital and teams of people that need to have a say in how it's designed, how it's going to operate. So there's the nursing staff, the lab staff, radiology staff, surgeons, which have a lot to say in how things like operating rooms and stuff will function. The physicians, doctors themselves. It's important to think about the patients and what will they need. The operation and teams of the maintenance staff and those people. And then of course the owners and the owners reps, what's important to them for operating the hospital. And then as far as regulations go, most states will have an AHJ or authority having jurisdiction. and they'll have specific requirements for hospitals. Perhaps your particular state has requirements on energy savings in a hospital, or have specific requirements about air changes in a hospital that are slightly different than others. Those are very important to talk to and know what those are. So if you can bring these stakeholders together and get them to, assign priority to metrics, it can allow you to make decisions. So for this example, hospital, let's say I brought all those people together, we had a discussion, and we really decided that patient outcomes and carbon emissions are the two things we care about for our hospital. And that's what we picked here. The answer for some hospitals could just be cost, because they have a very small budget and they just need this hospital built to help underserved community. That could be the answer for a hospital, in which case the answer in our final optimization would be different. But here I'm going to take patient outcomes and carbon emissions. So those are my kind of focus metrics or focus outcomes. And so what I'm going to do is maximize my SDA, because I'm going to equate that to patient well-being, and I'm going to minimize my embedded and operational carbon, because we're going to reduce emissions as much as possible. So to do that, we're going to select option 3, which is this U-shaped building, and we're going to kind of continue on our analysis with this. I did put this note about other design aspects, because in all buildings, hospitals included, there are other things to consider when you're selecting your mass, not just the exact EUI, the exact solar. That has to do with site context, neighbors. Does the building look the way it should look? All those things, and those are important too. And all analysis should feed into and help those things kind of be optimized. But at the end of the day, we're not just doing academic designs of buildings. So other things do come into play that might override some of the settings that we would look at here, like EUI, etc. So moving forward, we're going to do some site rotations, because I have a very empty site. So in theory, I could put this building any way I want to on the site. So just doing the typical 90, 180, 270 degree rotations, I get my results again, and there's not much difference. So my EY is pretty steady. My SDA is pretty steady. My costs are pretty steady. In this case, InBody Carbon is exactly the same, because I didn't actually change anything about the envelope when I rotated. So where does this put us? How can we make a decision with this? Well, the important aspects of these modelings is that they offer comparison, and that means they're not always conclusive. That particular study showed that rotating the building did not have a big enough impact to make a decision, and that's okay. What I would advise is always avoid the temptation to add decimal points. If you look here, I'm only going to 7.6 million. If I added more decimal points, I could show a change in all of these. They'd be very different. But in reality, we need to remember how accurate these models are, at the stage we're at. 7.6 million, I'm confident in that number. Anything beyond that is essentially noise. And filtering that noise out, for decisions is very important. So again, how would we make a design decision at this stage of the rotation of the building? It often comes back to those other design aspects. So in this case, maybe the site works much better, rotated my original direction. So we're going to proceed with that. Maybe that lined up with the road much better than any of the other rotations, and that's okay. We're going to go on that path. So kind of on that note, some helpful tips on kind of doing these early stage modelings. It's don't get sucked into the details. Reheat and humidification are end uses in a building, especially a hospital, and they will have an impact on the total energy use. However, I'll argue that the options that we're looking at here with rotations, different massing, aren't impacting those two end uses directly. And so we just need to know we need to study them later when we have the level of detail required. And that's going to be, all the zones of the building, how the HVAC system is zoned, what's the source of the humidification. And then we can study those things and minimize them. But at an early stage, it's important not to get distracted by them and allow yourselves to make decisions with the information you have. Again, getting that buy-in on what the metrics are going to be to drive the decisions is important. If you have a project where you start out and you assume emissions is the most important, but you haven't got buy-in from the whole client team that that's the case, your decisions can become null and void very quickly, where it might turn out that cost was the most important factor, and that needs to rule all decisions. And then it's important that modeling meets real-world needs. And this kind of gets down to glazing. So we're not going to look at a window-to-wall ratio study for this building, and that's because glazing should really be responsive to the space beyond. So if I have a wall of my building and that's all the wards, it should have glazing that's responsive to the wards, to the bedrooms, that gives proper daylight to those. And really, if I just looked at percentages on each wall, I'm just confusing things, and I can get down a rabbit hole where the actual answer to the window to wall ratio study that no one wants to hear is that no windows is the most energy efficient. And so just kind of avoiding that whole aspect can be helpful, and letting glazing be what it is, like for the people beyond, and have it be designed in that fashion can really help. So now that I've picked a massing and a rotation, we're going to look at a bunch more options, so some technology options. So here I have 22 different technology options that we're going to look at, and these cover the envelope. So we're going to look at some wall values, some glazing U values, and shading coefficients. The roof value, will a better roof help us? Then some HVAC options. So what if I add energy recovery? What if I change up my system type? So I started with a VAV, water-cooled chiller, gas boiler. What if I did an electric boiler? What if I did an air-cooled chiller? Does that change anything drastically? And then operational ones. And these are very critical for a hospital, because operations of a hospital can impact the energy significantly. But these, again, they need buy-in from those key stakeholders. If the hospital needs to be open for the surgeons 24/7 or the nurses 24/7, what have you, then it needs to be so. So we'll look at kind of a case around that in a second. So these are the options I'm going to study. It totals 304 different combinations. And so what that looks like once we run them all. So we're running on a U-shaped building at a rotation 0, because that's the two things we picked. We see our 22 options on the left and some performance metrics on the right. Kind of right away, what we're going to do is just throw out anything that isn't better than the baseline. So again, I had over 2,000 combinations. I don't want to see 2,000 combinations. I'll never get through the data. So we're going to throw out anything that didn't perform better than the baseline in terms of EY, carbon, or cost. So if it didn't beat them, at least one of those categories, we're not going to look at it. So that leaves us with 98 in this particular study. And so going back to the requirements that we identified for the project, minimizing embodied carbon is what we want to do. So we're going to select for below 600 embodied carbon and look at what options we have. So we still have 21 after that, which leaves us some room to pick some different options to see how else we can go. But if we look, we actually see we have this line here where we appear to have something at negative cost premium. So let's check that out. So we found a bundle where if we reduce the night schedule, so in this case, reducing occupancy down to 60%, say some wards don't need to be open at night because it's not as busy, hopefully, etc., stuff like that, we can really save a lot of energy. So doing that and then actually reducing the building performance of the wall insulation allowed us to save some embodied carbon, save a lot of cost, and still have some energy savings. So still 1% energy savings. So this is an option that we could do to save the project a lot of money and still save a little cost or a little energy. However, because that's an operational thing, maybe our key stakeholders come back to us and say, well, we can't turn down at night. We need to be open at night. We have a lot of people come in at night for various reasons. We can go back to the drawing board and say, okay, well, let's lock in that we're going to use our baseline occupancy schedule. We're not going to even look at that. And that leaves us with just 6 bundles left that are also below the 600 embodied carbon, so reducing that embodied carbon. If we then kind of pick and say, well, what else are we interested in? Let's save as much energy as we can. So if we select for the maximum energy saving, so here we have about 8% or 9% savings, and that gives us a single bundle. So now we have our optimization based on the metrics we defined it as important to us. So embodied carbon, and then energy savings, and SDA is kind of already locked in because we picked on mass. And to do this, we have a cooling setback, reduced performance of that wall again, which helped on the embodied carbon side of things. We increased the glazing performance, and we actually switched to an electric boiler. So now we're all electric, which is great for our carbon emissions on site. And so, and the cost premium for that is not much at all. So only 41,000, which for our original estimate of 7.5 million is not much at all, and allows us to get a UI of 218. So pretty good optimization. So to recap, kind of what have we done? We started with an idea of a new hospital on a site. We looked at 3 masses, actually not 5, sorry about that. And then we picked the mass that had the best STA. So that was the U-shaped building. We did 4 rotations, and we saw that the rotation did not have a big enough impact to make a decision. So we let other factors make that decision for us. We decided on the original rotation because that worked better with the existing roads, etc. We then picked 22 technology options and looked at all of those. That was over 2,000 different bundles of options, of which 98 were successful. And successful, I'm saying that they saved energy or they saved cost. And from that, we picked our optimized solution, which got us an SDA of 26%, which is pretty good for a hospital with really deep floor plates. That really what makes SDA a struggle for a hospital project. We reduced our embodied carbon below 600. Our EUI is 218, and our construction costs, at 7.6. We really didn't, change that number at all. So that's the outcome, starting from, essentially an idea, going through the steps of what do we need to optimize, what's important to us, and getting to the answer for our specific project. And again, this answer would be different if the requirements for the project were different. For example, if construction cost was the driving factor, we might likely see a much lower SDA percentage as the result, and maybe a higher embodied carbon actually, because they don't always coincide, and maybe a higher UI, or you might have even seen a lower UI, etc. But that might have had a much lower SDA. So it's all about deciding what factors do I need to optimize for, and using those to make the decisions at each step. So again, to recap, so we did a lot of work there. There was already over 2,000 models run. How long did it take us? So a traditional method might take us like 160 hours for the daylight, the glare, the facade, the HVAC, the carbon, all of that. But in reality, for this particular case, I did it all in essentially 8 hours and the PowerPoint. So we can do this very, very quickly. And that's important, not only to save projects teams money, save projects themselves money, but also to get answers into decision makers' hands when they ask the question. And that can really go a long way to getting decisions made. If someone asks a question Monday, it takes you 160 working hours to answer that question. That's a couple weeks away. They're going to forget what that question was, and suddenly they have different priorities. Making that decision is very, very hard. If we can speed up that response time of answers to questions, we can really help not only the bottom line of projects, but also get those decisions made. And so, of course, this was concept design or early stage. Where do we go next? There's a lot more to a hospital than this. So I would kind of some next steps I'm suggesting, and these are also connected to that targeting 100, which I definitely recommend people check out, is to first minimize reheat. So reheat comes from the zoning of a project, how are rooms that might be cooling and heating at the same time zoned together. Getting really good zoning will help. That means, tying with your mechanical engineer as the design progresses and making sure the zoning is as good as it can be. Good controls also goes a long way to reducing reheat, and exploring options like fan coil units, or et cetera, that decouple ventilation from conditioning can help as well. Implementing heat recovery on anything and everything that you can will also go a long way for a hospital project. One watch it here, of course, is that the simple approach you might do in an office of throwing an enthalpy wheel in your HU isn't always an option with a hospital, because mixing, potentially contaminated airstreams with supply airstreams is not allowed. It's not safe for the patients. So there's a lot more complications there, but it's still a very key energy saver. Reducing system loads is another one to kind of target next. And this again goes down to working with the mechanical engineer, working with the architect, because this gets down to the fan energy that we're looking at. So fan energy was over 10% of the building. We can reduce that by having lower pressure systems. Lower pressure systems need more space in ceilings, in risers, etc. So there's a trade-off here. Do we have all the space that we want in the building for other things? Or do we keep those ducts right size so we don't induce pressure drop that use more energy year in, year out? So that's something to focus on with the team. And then there's reducing zone loads. And this gets down to your lighting and your equipment. And this, again, can go directly with those key stakeholders. So what equipment is everyone using? Is there, do people turn their computers off when they leave? Is there stuff that can be turned off? Is everything just left on 24/7, whether someone's in that, wing of the building or not? Those kind of operations things can go a long way to saving energy. And of course, all these things need to be considered while maintaining safety. So COVID has certainly brought to light the importance of fresh air in buildings, even natural ventilation. And that needs to be considered when doing any of these things. That anything that is done that might reduce airflows or do something else to the indoor quality of the space, that it's still maintaining safety for the patients, and the staff within the space. So that's kind of all I had today. I want to thank everyone for listening. I think we'll open it up for questions from the group. Oh, yes, I can confirm this is being recorded. Yeah. All right, doesn't sound like there's too many questions, which is all right. I hope this was kind of informative and helpful for anyone that's either working on a hospital project or working on different projects. These things certainly work for any project. I want to thank everyone for joining in. I guess I'll check in with Mike if there is anything else to cover at the end of our webinar.
Nope, I think we're good to go. Don't hesitate to reach out, ask questions if they come to you afterwards. This video will also was recorded and it'll be available on YouTube, and we will share that link out with everybody that registered. So have a great day. Thanks again, Patrick. Much appreciated.